trying to keep time. All right, thanks. And thank you, Marsha and FX, for letting me talk in this. I feel very privileged. Yeah, it's been stressful for me, because the most stressful part of this workshop is try to sort of adapt your description of the KSD as you see other people described it. And then like in my attempt to do that, I realized that my set of slides sort of degenerated quite quickly, and it rendered to like from a set to a point, and then it made the talk trivial. And then so I added all the space fillers back. So a lot of the KSD description, they're just space fillers, just to make the talk look non-trivial. And then, but yeah, so we did, so anyway. So that's why, so the point is I'll try to go through the KSD stuff quite quickly then, because I think brilliant people describe it in various different aspects. But for just quickly give like a summary, maybe like what's been happening. So you have the Stein discrepancy, and the Stein discrepancy it's just a statistical discrepancy, so that it compares the distance between two probability measures, P and Q. Oh, by the way, the work was initially called Stein Q, important sampling, but then we realized the clashing notation of Q people usually use to describe the approximating measure, so we call it Stein pi to make it a little bit different from P. So P, pi, just the differences in I, important. So anyway, so and then I realized when I was preparing the talk, this nice acronym, the algorithm now becomes SPICE. So that was quite nice. Anyway, so that's KSD, just measures the difference, and if the two measures is the same, you get zero KSD. Sorry, you get a zero Stein discrepancy. And in the and it's quite useful because I think in the workshop people have covered both sides, right? So you could use this to do posterior approximation, like sampling, which is mainly what I have been working on in this field. So the idea is to minimize the Stein discrepancy by finding a nice Q that makes for example, the KSD small. The idea and there are various ways that you could do it in a non-parametric sense. Like if you want to do like particle-based approximation of Q, then you basically somehow get a set particle and then select. You either do like a hard selection, so you do like a subset selection, or do like a soft selection, which basically is like reweighting. So this is a hard selection, and then that's a soft selection. Or you could do it in a more traditional variational sense. Or people have also talked about dealing with intractable likelihood. So in that case, your PN, this guy, the approximating thing is actually your data. So you treat the data as a discrete set of points, and then the target becomes your model that depends on some parameter, and then you choose a parameter to also shrink the discrepancy. Hopefully, you get good model fit to the data. So yeah, that's roughly what's happening. And so this is Stein important sampling. So this is not pi important sampling yet. So just to set the scene, Stein important sampling is that where what you do is you generate a whole bunch of particles from some proposal distribution, which is P here, the bold P, and then you compute the optimal weights W star in such a way to minimize the weighted discretized states, the weighted states, which is just a set of points you can think of. So we're trying to optimally to get a whole bunch of particles, right, from some proposal distribution and reweight them to minimize the Stein discrepancy. And the output of the algorithm is just a weighted set of points. So this is Stein important sampling. So you can generate, basically you can imagine that this thing can go horribly wrong if you generate from a proposal that is way off, right? So then you don't get enough sort of candidate states where the target has a lot of mass. So you basically want to construct it in such a way that the interesting parts of the target distribution gets a lot of points, so that there's a lot of like way to reweight them, so that the reweighted bit can be sort of have a high enough resolution to approximate the target. Yeah. So and this has been studied, and people establish like conditions for consistency for such algorithm, given that so let's say pi is now your proposal, so you want to replace this guy with some distribution, and providing that these are not so different, then we're all good. So the question is then, how do you choose a nice pi so that after you reweight them, you have sort of like a, there must be a sort of a different layer of optimization problems. So this is one layer of optimization, but on top of that, you want to select. So here, the more general optimization problem is how would you then select a nice proposal distribution that also after you with reweighting say the states from that proposal later in mind, how would you select that proposal so that you get a nice approximation basically. So yeah, and this thing just to show from the Stein important sampling paper, these people have generated like a Markov chain from an unadjusted Langevin process, and obviously that is biased. So if you calculate KSE MLD, you will not decay. So that's a blue line. But if you do your reweight by different base kernels, so you have the Gaussian or the inverse multi-quadrate kernel, you seem to, the approximation at least seems to now decay, and the IMQ is better than Gaussian for reasons that we already know. And then, so this is sort of the convergence rate that they sort of in the paper they shown, and then and that's exact like IID sampling. So this is better than IID. It's just because doing this instead of bias removal, you also get like a variance reduction. Yeah. All right. So the brilliant minds behind Stein pi importance sampling are as follows: Congyi Wang in the audience, Hishiro Kanagawa, and Chris Oates. Okay, so very quickly, KSD. So you have a kernel, and then gives you a reproducing kernel hyperspace, and then you can embed the distribution in that space. And the way you embed it is as follows. So mu of p is the mean element in the reproducing kernel hyperspace. So yeah, so that's the embedding of p. And then the idea about the embedding is that, the nice thing about the the niceties of this KSD is that this just becomes the RKHS norm between the approximating distribution and the origin or the zero function. So that's why, because we're not always comparing to origin, so we remove the dependency on the true on the target, because the target is encoded there. You can also interpret it as a integral probability metric where it gives you the worst case approximation error under class of functions. And as people have talked about, if you make that class function really nice, then what you can do is the Stein allows you to remove the dependency on P. The kernel allows you to get rid of the soup. So that's sort of how it works. And then now, so how to then choose pi's, right? So the initial sort of venture that we set out to do is to choose a nice pi. And this problem turns out to be quite difficult, actually. So if you want to think about choose pi to generate some states, and then you're going to reweight the states using W star, then this problem can be quite hard because it depends on like kernel, and it's no obvious way to actually frame it. And the way that we did, somewhat ad hoc. So we we know, right? So the logic is that we know with respect to KSD, if you choose W star, that gives you P star, you're going to get the lowest. You're going to get you're doing the optimal thing with respect to KSD. But any other set of weights is then less optimal than that. So that sort of gives you a bound on this. And then it's really hard to work with this guy. And then we're trying to work with this guy so that somehow if we can make this better, hopefully we're doing the right thing. So hopefully there's a lot of sort of not very tight connections there. So that, but as we'll see, what happens? So we basically reframe the problem itself, so normalize the importance sampling. And in the actual algorithm, we don't actually use any importance sampling. Like we don't actually use the traditional importance sampling as an algorithmic construction. This is just purely to derive a nice form of the proposal. So this is like a theoretical tool to construct the proposal. It doesn't actually get into the algorithm. So the way that we think about this is, how about if those W stars is too hard, then how about we think about W, which is given by us by self-normalized importance sampling. And the reason, because we want to measure approximations, so we want these things to be all positive sum to 1. So that's basically the construction. And then we think about, okay, what does that mean in terms of, because we want to mean, so the goal is to minimize KSD. So what does that mean in terms of, how do you rewrite KSD using that set of weights? So that is basically the KSD, and that's a kernel embedding. And then what you get is you realize large numbers, the denominator converges to 1, the numerator converges to Gaussian. So you get something like this. And it seems sensible to then think about what is the best way to do here. So what we do is, so that's just the covariance operator. And if we think about the trace of that covariance, that gives me a sense of like the variance of this thing, and we want to minimize the asymptotic variance. So that's exactly what we did. So we're gonna go minimize the trace of that covariance, and it turns out, due to niceties of this space, this thing works out quite nicely, and your density pi, the density of pi, just proportional to the square root of the diagonal of the kernel function. So basically, pi is proportional to the density of your target modified by this guy. Yeah. So you basically have something that's intuitively you basically end up with something that's similar to your target. So obviously, if pi is extremely different from the target, then things will go horrible. So intuitively, even if you don't do any of this, you should construct a pi that is similar to your target, maybe slightly fatter, slightly sort of tempered, right? So and we were trying to sort of understand. So yeah, so if to actually run the algorithm, what you do is instead, so before when people do the reweighting, they will run an MCMC to target P, exact target, and then they will post-process it by reweighting it to remove any bias introduced by the MCMC. Yeah, and then so what we're telling you to do is that instead of targeting P, you should target pi. So you should design an MCMC not to target your actual target, to target a slightly modified version of the target, and then you reweight, and then you'll get better approximation, basically. Yeah, a lot of these. Okay, so this is your P, and then once it's under different types of sort of most recently investigated Stein kernels. So that's just the long-driven. That's just sort of the traditional one, the IMQ kernel, and the KGM Kanagawa, Breton, Mackey. So that is the moment control Stein kernel that controls up to a certain moment, and the Riemann one is where the Stein kernel comes from a diffusion process that hopefully is mixing a little bit faster, and then theoretically that should get you a tighter sort of convergence, a better sort of tighter bound on the convergence, hopefully. But that thing's really hard to calculate, so we just do it as an exercise. We were curious, but practically speaking, these two is what we actually use. So that if that's original, that's just from a regression problem with 2 parameters, and then turns out is the image is posterior. So that's a high density, that's low density. And then once we do this modification, you see that it is fatter. And it also introduced, so this is real, like some sort of dip in the middle. And so what actually happened is if your target has a lot of density at some region, that means if you're actually generating from target, you're going to generate a lot of points from that region. But a lot of that point is sort of wasted in a way. So you should give some points from the middle to the tail. And then that will give you better approximation at the tail. And you have enough points in the middle anyway, so you probably don't need that many. And then under different kernels, the shape can be quite weird, and we can't quite make sense some of why the shape look like that. But I'll give you a simpler picture. And so now these things are not quite comparable. So this plot is a bit weird. So you compare blue with blue, purple with purple, red with red, because they're all under different types of KSD. So you're hoping that this dotted is better, because this is by sampling from pi and then reweight. This is sampling from p, then reweight. So you do get improvements. And so this is on a two-dimensional problem. And this is another, I was just trying to see, because the KGM kernel picks up, ideally controls convergence up to third moment. So if you have something skewed, so that's a third moment. So if you have a skewed posterior, what happens to the KGM kernel? And then, so basically that is the pi. So as you can see, it took away some points there, and it gave it to where the distribution kind of decayed really sharply. So here it probably needs a lot of resolution to approximate it quite nicely. So that's how we kind of intuitively make sense of what's actually happening. And we compare it to something that's optimal under the 1 versus sign. That's orange. So it seems, so what the under 1 versus sign, the optimal thing here is just to temper it. So take the square root of the original density, makes it a bit fatter. It seems that, yeah, it's doing something than just making it fatter. But if you actually plot the KSD, you do get an improvement over the 1 versus sign way, which is an obvious way of tempering the original distribution sample from. All right, so is this inconsistent? I'm going to go quite quickly, 3 minutes left. So yeah, so we did accept. So if you actually, we essentially expect consistency if you actually use Mala to target pi. So spice Mala, we give you consistency, and the result we basically combined the results from one of our previous results and the set of newer explicit conditions for Mala. And then so the nice thing is we run this stuff. Does it actually work in practice, right? So we run this stuff on the whole what's called the posterior DB. It's invented, well, not invented. It's constructed by the people that involved with Chen. And then the idea is to add difficult or standard or sort of the type of models that people usually fit using Bayesian to a database. So you have, they have like a database of posteriors of practical problems that people actually do in various fields. And so we just basically took that database and we run the algorithm. So that's Mala, you're looking for red. So more red is better. So that's a standard. Obviously, you get improvement just by running the importance sampling targeting P. And then you get improvements by running this in targeting pi. Under 2 different sets of kernels. That's why, so these are not comparable, but these 3 columns and that 3 columns are within themselves comparable. And some of this, so that's a dimension of the problem. So so we were happy to see even for some of the higher dimensional problems, we were showing advantage because, yeah, so intuitively what happens is that for higher and higher dimensions, the difference between P and Q will reduce. And the difference between P and Q are smaller if your posterior is Gaussian-like. Okay, so just to summarize, what we have done, I just talked about what we've done. So what will be interesting to explore is the interplay between the choice of sign discrepancy and the sample. I'm interested in sampling, and the different sampling methods, and also, you know, KSD is quite expensive to compute, so I like to work on reducing the computational cost or think about spaces other than RD, like sampling in that. And that's our archive paper. Thank you very much.
We have time for one question. question? Thank you. Very interesting talk. I wondered about networks when you said extend to the spaces beyond RG.
Yes. I haven't thought about networks. Yeah, so.
Cool. If anybody else has questions, you will get a chance to catch up with the speaker in the conference slot. Thank you again.